right, we're just going to give everyone just a few moments to drop on in. Tune in live, because right now they're receiving notifications that Tech Art Talk Live is now commencing. All right, I assume everything is going well. All right. Very good. All right, well, let's get this show on the road. Welcome, tech artists from around the world. It is 12:30. It is Friday, and it is time for another episode of Tech Art Talk Live. My name is Chris, and I am going to be your host for today's session. Now, last week we started our first in our post-production series when we were dealing with visual effects driven by post-process effects. Now, last week we were dealing with other issues, and this week we are going to be dealing with special effects. They're most focusedly dealing with blurring. Now, blurring, what does that mean? Well, actually what this is we're going to be using something called a convolution filter. Now, last week what we did was we were working on filters that were driven by standard matrices, which applied color adjustments to the entire image. Now we're going to take that concept again and we're going to apply this to something called convolution. And you're probably going to me like, hey bud, what do you mean by a convolution? You know, that doesn't make any sense. And so let's get on with the talk about convolutions. Okay, now convolution filters are little filters that are applied by little blocks of size. Neither maybe like 3x3, 4x4, 5x5. They're usually square, same width, same height. And what they do is there's a central pixel right in the middle of like those. So it's not going to. It's got to be some kind of odd number, like 3x3, 5x5, 7x7, 9x9. And you're going to take that center pixel, and that center pixel is going to average or do some kind of mathematical operation to all the pixels surrounding it, and do the variation of whatever mathematical operation that performs, then it is going to apply to the color value of that pixel, and that is a convolution filter. Now, convolution filters can be done with a bunch of different things. Now, what we're going to be focused on today is primarily image blurring, and we're going to be dealing with other things, like we're going to give a demonstration today about bloom. We're going to be dealing with depth of field, and we're dealing with lens flare. These are the kind of focuses of today's lecture. Now, blurring is done with multiple different strategies. There's more than one way to do a blur, and we're going to be covering a couple ways of doing blurring, because blurring is pretty much a must-have in any visual effects arsenal. Let's see. There are several convolution strategies. There's mean filters, weighted average filters, and Gaussian filters. Today we're going to be giving demonstrations on mean filters or box filters. We're going to talk about a little bit about weighted average filters, and then we're going to be also giving a demonstration of what Gaussian filters are. You're probably going, ooh, Gaussian. Okay, now mean filters are just simple box filters. They're little things that they're just averages the current pixel value with its nearest neighbors. Like if you have a 3x3 matrix, it's going to average all the pixels surrounding it, and that's going to give you the 3x3 average of this center pixel. If you do the same thing by 5x5, it's going to average the nearest 24 pixels.
So how did you like this?
All right, so what we're going to do now is we are going to focus in on our demonstration here. Okay, now we're going to be using the straightforward background that we used in last week's lecture, and we're going to pass this on just a little bit further.
Half of it is mostly Blender, half of it is just my
All right, so we're going to start off here by we're going to create a brand new shader. So let's create an effect, and we're going to create this, and we are going to call this convolutions.
Yeah.
Okay, we've got convolutions here. All right, we're going to first start off with our resources. I'm going to drop that in here.
I think I will just pick this one as one of my works.
Oops, didn't mean to do that. Get this back. No. Oh, we lost our shader tool. How about that? That's not fun.
The only thing is like getting to this point.
There we go.
Making sure everything.
Sorry about that. So let's get things going here. And let's get things, create another effect here.
Yeah.
And then once again, I'm going to call this
I
convolutions.
think that's what you need to work toward. What about stuff that you made while you're here or anything?
I'm going to be working more retexturing on my.
All right.
break.
Now we're going to be starting with
That's
the
going to be,
resources here.
My final piece for the interview.
You could potentially show.
All right. Let me see if I can expand this up a little bit.
And just talk about like, hey, these are not my assets, but I'm trying to learn how to, do environments and stuff. Right?
Ah, there we go.
I think it'd be worth it.
Blew it up just a tiny bit. Wasn't able to blow it up too much. Okay, we're going to start off with this very simple. On a C buffer per frame, we're just going to end up worried about what our box size is. Okay, what kind of box size we can work with? Now, we're just going to be averaging the amount of filters we're using, but we normally work with things that are of odd number, maybe 3, 5, 7, 9. We're going to be focusing on that, but we're going to create a floating scale so that we can modulate our box size. And then we need to know our viewport size. Why? Well, I'll show you in a little bit, but we need to know how much to scale our pixel amounts by, because we're not going to be dealing with the entire viewport. Well, we're going to be entire with little windows, and we need to know what our viewport size is. And then we're going to deal with our render target. Well, this is it, a render target. It says right up here, a render target. Now this is our background image. Now this is what's coming out of the rendering pipeline, and we're going to be taking that and we're going to be performing operations and convolution filters upon our render target. And here's our sampler state, and we're just going to create it as the minimum, the magnification, and the mipping. We're going to make that linear, and our addressing in both the U and V directions is going to be wrap. So we're going to deal with our data structures next. Now our data structures are going to be super simple, because really, once again, we don't really have to worry about transforming our geometry into worldview projection space. It's already in there, gang, so we don't have to deal with that. So all we have to deal is, as far as input is concerned, we have to deal with object position, and then we have to deal with the texture coordinates. And then we're going to take that into our vertex shader, and then we're just going to pass them right through. And so that's why our vertex shader output looks exactly like our vertex shader input. So let's take a look at this increasingly simple vertex shader. This is going to be the same vertex shader that we used last week, and so it's not going to be doing a whole lot. All right, so here we have we're going to get our vertex shader input. We're just going to zero it out to begin with, and then we're going to take the position, pass it on through. We're going to take our texture coordinates and pass it on through. All right. Unknown callers trying to get through to me. Very strange. All right, so let's worry about the pixel shader next. Now the pixel shader is where we're going to be doing all of our magic. Now the pixel shader is a little bit complicated, but really the mathematics are pretty simple, because we're going to be dealing with a bunch of for loops. All right. So here it is. This is really just a lot of setup. We got our vertex output coming in, and then we're going to create a buffer variable for ourselves. We're going to call it sum, and it's going to be a flow 3. And so this is where it's going to store all of our averages. And then we have to compute the scale. And the scale is how big our actual texels are. And we're going to take that by dividing 1 by the viewport size. Now the viewport size is totally dependent. It might be 1920 by 1280, and if you have a smaller display, it might be 256 by 256 or 512 by 512. We don't know. But we're going to take that viewport size, and we're going to divide it into 1, and that's going to give us our texel scale. And then, as we go through and average all of our pixels, we need to know how much to increment them by. And so what we're going to do is we're going to take our box size, and we're going to divide by 2. And once again, our box size is what we are set up here in the inside of our C buffer per frame. We're going to take that box size, divide by 2, and then we're going to create an offset. Now this offset is actually going to be doing the actual offsetting inside of the U and V direction. And we're going to start things off by just doing a sample of the color render target for our central pixel. And then what we're going to deal with is when the box size is 0, we're just going to return it. So if the box size is 0, we're just going to say, hey, bud, we don't want to see anything. Just leave it at 0. Then we're going to create 2 for loops. One in the horizontal direction and one in the vertical direction. And all we're doing is going from 0 to box size. So if box size was 3, we're just going to go 0, 1, and 2. And if this box size was 5, we're going to go 0, 1, 2, 3, and 4. All right, we're going to do that both in the horizontal direction and then the vertical direction. And then all we're going to do is compute what our offset is. And we're going to create that by just saying that our offset is going to be the I minus the increment and J minus the increment. Remember, increment is what we computed by taking our box size over 2 and then doing the floor of that. And then that's going to give us our offset, and that's going to change for every frame. And so what it's going to do is we're going to create since this is a box, it's just going to take all the pixels surrounding it, and then we're going to do this. This is like an n squared algorithm, and then we're going to do this. We're going to sample the background. We're going to sample our render target, the box size by box size 9 times, and then we're going to average all those values, and then we're going to take that average, and then we're going to divide it by the box size times the box size, or the box size squared, and that's going to be our X, Y, Z, or red, green, and blue values. All right, so that's what our pixel shader looks like, and I'm going to finish this off with a technique for this. Okay, so we've got our convolution filter, so let's go ahead and hook this thing up. Now, since we're already working with the existing pipeline, we need a new draw command. So I'm going to go here and look over my scene and create a new draw. Okay, and then for my input geometry, I need just a full screen quad, or in this case, a partial quad. All right, now our box size is going to be a slider. Let's go somewhere between here. Let's go between 0 and 9. And hook that up to and then our viewport size. Now, viewport size, that can be a variable critter. So what we're going to do is we're going to let the system decide what the box size is. And so here I'm going to go for this, and I'm going to go, okay, is this my box size, target combiner to, okay, the scene, okay, viewport size, here we go. I'm going to go ahead and plug that right in here. And then our render target is going to come right from our prior rendering in the background, right into here. All right, so that's going to give us our box technique. And let me get a new render target viewport. Plug that right in here, and we see nothing absolutely changes. Why is that? Because we created a situation of where our box size was 0. It does exactly nothing. And so what I do is I'm going to increase this to 3, so it's going to be 3 by 3. You'll see that it blurs just very, 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 very so slightly. But if we increase this to some other number like 5, it's going to blur a little bit more. And then we do it all the way to 9, then it's going to blur a whole bunch. So you really have to crank on that box blur to really get it working. But since we're doing this both in the vertical and the horizontal direction, we're getting some kind of good blocks behavior. And let's see if 7 looks any better. Yeah, it's a little less. That's pretty good. And then we go 5. Oh, that's right. I forgot about this. This is Shader Tool, and this is one thing. Yeah, even though we're typing this in here, the value doesn't really change. How about that, folks? That's really a bummer. That's too bad. So we had to do it. But the thing is, if we go between even numbers, the value flashes. Why does it flash? Because it doesn't really subdivide very well. So there it is at 3. And this is at 5. And get 7 in here. There we go, 7, and then finally 9. All right, so a box filter is a good, cheap, and relatively fast filter that is fairly influential. Now, it works okay, and for as a regular filter, it works pretty good, but there are better ones that can be used. And one of them is a weighted average filter. Now, a weighted average filter is cool because what it can do, it's like a box filter, and it's pretty cheap, but it gives more weight to the center pixel. And so what it does is that all the pixels have to weigh into a value of 1. So that means that the pixels are going to be somewhat normalized. And that gives us more control for the central pixel. And it kind of looks like this. If we're going to multiply the color value of all our surrounding pixels, if it's a 3 by 3, by 1, and then multiply the center one by 2, then notice then when you add all these up, they're going to equal to 10. So when you divide that by 10, 10 by 10, that equals a value, the sum value of 1. But notice that it puts in a little bit more oomph, a little bit more punch into that center pixel. And that's what gives it just a little bit more definitiveness, because box blurring tends to be kind of, well, for lack of a better term, sloppy. And it's just effective. And if you don't know what I mean, look at the new, or it would be a Windows 10 kind of like a view screen at the beginning. If you just allow it to just log in, the whole background blur. And I think they're using a box blur because box blurring begins to have a kind of a presence after a while. It begins to look rather similar. All right, now what we're going to be dealing with is, instead of a weighted average filter, we're going to be dealing with a Gaussian blur. Now, Gaussian blur, admittedly, are kind of expensive. They're it's a 2-pass filter, just like the box and the weighted average. You're going to be working on the horizontal and then the vertical, and then each row in each column is averaged over a kind of a Gaussian curve. Now, a Gaussian curve is a simple little bell curve, if you can remember that. And in case you haven't forgotten, or in case you happen to be a statistician, yep, this is the formula for a Gaussian curve. Look at this nasty thing. And I'm not even begin to announce this, but this sigma value here corresponds to the amount of blur that we actually want to see. And what we do is we do 16 pixels in a horizontal and then 16 pixels in a vertical, and we pass all of those onto a Gaussian curve. Now remember, the Gaussian curve looks like something like this. It's a standard bell curve. So that means if we're going to be doing 16 pixels across, that means the center pixel is going to be getting the most amount of weight, and while the pixels on the edges are going to have the least amount of weight. All right, and I'm going to go ahead and work on this, and we're going to create a actual Gaussian filter. I'm going to return back to my display here. And then we're going to start off by adjusting our resources. Now, where is it? Oh, here we go. I'll scoot back up here. Now, we're just going to make adjustments to our C buffer per frame. And so, in addition to our viewport and our box size, we're going to be adding a float value for our sigma. And then we need to know what direction that we're working on. We need to know whether we're working on a horizontal or a vertical direction, because we're not going to be doing both passes in the same call. We're going to be doing one for the vertical and one for the horizontal. And so that's why we need to have a U direction in order to identify the difference between the two. Now, in order to help this along, what I wanted to do is create a utility that will actually calculate that Gaussian formula for us. And with that, I'm going to create this little Gaussian utility here. It means calculate Gaussian, or calc Gauss. And the input is x, which is the current pixel value, and sigma is the actual curve value here. And now remember, sigma is going to control the amount of blurring that actually happens. Now, if the sigma value is 0, we're going to leave that at just plain old, or we're going to return nothing, and we're going to blur nothing. But here it is, gang. Here's that ugly little formula that I showed you earlier, and here it is in its splendor and glory. All right, get out your screen capture devices and your cell phones and take a picture. Everybody wants to know what the Gaussian formula is, and there it is. All right, so let's take a look at our pixel shader. Now, our pixel shader is, it's going to be just about as difficult in complexity as our box filter, but it's a little bit different. All right, so let's take a look at our Gaussian pixel shader. All right, we're first going to render the center pixel, we're going to get that from our render target, and then we're going to get its Gaussian color value. All right, so we're going to take the float for our color RGB, and this is going to be our central color. And then we got to know whether we're going in the U direction or the V direction. Now, if we're going in the horizontal, then that means we're going in the U direction, and that means the vector is going to be a value of 1, 0. Now, if we're going vertically, that means we're going in the V direction, and that means the vector value will have a value of 0, 1. Okay, that'll tell us the difference between whether we're going vertically or horizontally. All right, now we're going to, remember how I said that we're going to average the 16 pixels surrounded, and we're going to call that the number of iterations. And that's what's going to drive our for loop here, because we're going to go through the number of iterations. Now notice that in this situation we're not starting at 0, we're starting at 1. So therefore, instead of I as being less than the num its, I'm going to go I is less than or equal the number of iterations. Okay, we're going to first start off by going to take the value of our pixel, and then the value of our float iterations, and then we're going to send it to calc Gauss, which is going to do our calculation for us. Now, if the value of the weight is less than 1 over 255, that means it's too small to actually be displayed. We're just going to break and get rid of it. So we're not even going to worry about it, because we're getting inconsequential. But it looks like I've got a repetition here, and I'm going to go ahead and discount this because it looks like I've got this. Oh, I did this. Okay, so yeah, we're going to be doing this. We're going to be doing this twice. We're going to be going 16 in the right, 16 in the left, and then so therefore we're going to adjust our pixel sample bunch to the step times the float, and then we're going to go minus times the slope. We're going to go in the positive direction, we're going to go in the negative direction, and then we're going to add all of these to our Gaussian color. Then finally what we're going to do is we're going to divide the Gaussian color red, green, and blue. We're going to divide it by the Gaussian color W, which is the end, which will have the overall value together, and that's going to produce our red, green, and blue values. And then we're just going to pass that in with a 1 as the alpha value. All right, I'm going to go ahead and throw in a technique. Okay, give me my Gaussian blur technique. Okay, so notice that our shader now has changed a little bit. And so I'm going to change this so that the slider here is over at 0. I'll change this over to a Gaussian blur. Now notice that nothing has happened because we have to put in a value of sigma, and we have to come up with our U direction. So we're first going to be doing this in the horizontal direction. So I'm going to put down a vector, a 2 vector, and we're going to go 1 in the X or the U direction and 0 in the V, and so that means we're going to go horizontally, and our sigma value is going to come up with Oh, I forgot what the value range should be, but let's put it somewhere between 0 and 5. I believe 5 is just way too much, but better to be safe than sorry here. So let's go ahead and I'm going to go ahead and see if I can zoom this up a little bit, because I really want you to see this. As I increase my sigma value, you're going to see the background screen start to blur, but in a horizontal direction. You can see that it's blurring in a horizontal type direction here. And I'm going to change my maximum value here to just 1, because I think that should be more than sufficient. And it'll give us a little bit more control. And so we've gotten a whole bunch of blur by the time we go to Y. Now mind you that this is only going in the U direction. It's already going to be doing how. You can see the sides creeping in of where the blur is actually happening. And so in order to get a good Gaussian blur, we need to do this entire process again. And so let's go ahead, and we've got our convolution. Let's create a new draw filter, a new draw call. We're going to drag this down here, and we're going to drag our quad into here. And then our box size is actually our box size, we're going to leave that, but our viewport size we're going to need. Our sigma value is going to be the same sigma value that we've got from before. And we need a different U direction here, so I'm going to end up with another vector 2. And I'm going to make this 0 in X and 1 in Y. So now this is going in the Y direction. And for our render target, we're going to take the results that are coming right from our prior blur and drive that into our render target. Hello, come on. All right, there we go. So let's go grab ourselves a new render target. And there we go. Oh, we got a box blur, so it's thing. We have to make sure that this is Gaussian. All right. Oh, we still need a quad, because otherwise we're not showing anything. And there we go. Okay, remember, this is going to be horizontal, and this is going to be horizontal and vertical. So let's go ahead and increase our sigma, and you'll see that we get a nice, good horizontal and vertical blur in here. So remember, this first one is just being done horizontally. This one's being horizontally and vertically. And so we get a nice, big, good blur. And so pretty much as rule of thumb these days, Gaussian blur is going to be our go-to blur thing. Now, it's a little bit more expensive than box, and ultimately, if push comes to a shove and you had to really get efficient, then I would probably choose the box blur for being a little bit cheaper, and a lot of times that's all you need. But when you want your blur to be really good and crisp and really look good, then you're probably going to need to use a Gaussian. Now let's start talking about some of the other blur techniques that we have, because remember, you're going to use these blur techniques, but what do you use the blur for? Well, blur can be used for a bunch of things. Now, one of those things it can be used for is a lens flare. Oh, come on. There we go. Okay, now lens flares are actual real lens phenomenons. This is what happens in real life. So this identifies the brightest objects in the scene, and then check this out. It's going to duplicate those brightest objects 7 times. And then there's going to be a line that is based on the camera and the object position, and dependent on that line is we're going to line up those 7 copies all along that line, such that the smallest objects are in the middle and the largest are on the end. And this is really good for creating glass and trees and foliage and transparent objects. And so somebody asked me, like, oh, how do you go ahead and create one of these lens flares? Well, what you have to do is, do this, you go into your object, and then you take it, and then you isolate the brightest element in the scene. And then once you have that brightest element in the scene, then you extract it, meaning you make everything else black. Then you multiply it 7 times, and then you tint them various colors, and so you see the tint going on with this, and then again you take those 7 layers and then you blend them on top of each other, and then you paste that right on top of the original image. And so that is basically how you go ahead and create a lens flare. Now in this situation, I don't have it set up to make a lens flare, but it could be done if I had prepared the math in properly ahead of time. Now also something that we might want to do with a blur is a depth of field. Now depth of field is a little bit more complicated, but as you can see, what it does is it's based on the camera technology of where it takes the actual depth of field or the focal length of your lens. All images that are beyond the focal length will begin to blur, and all images less than the focal length will also begin to blur. And so only the objects into the scene that are at the focal length will begin to blur. Now, how useful depth of field is inside real time, it's variable. Now, in post effects, like in film, it's very useful, as it's used as a storytelling device. And when they want you to look at the screen and identify a particular object, then that object is going to be right in the depth of field. However, things are a little bit difficult in real time, especially in things like virtual reality, where we're not really quite sure where the user is going to be focused on. And so the use of depth of field is used primarily in things like cinematics and isolated issues where we really want things to kind of stand out and kind of like, dramatically glare at us. But, depth of field, it's a cool effect, but, used very, very, very sparingly. All right, so I'm going to go ahead and load up my next example here. All right, the next example I wanted to bring up is going to be bloom. So let me go ahead and get that. All right, now bloom also simulates the real lens affair. So let me give you an example of bloom here. So here's our original image here. And what we're going to do is we're going to isolate just the brightest objects into the scene. And then when we have the brightest object in the scene, then we're going to blur those elements and then kind of make them all fancy, and then we're going to layer them on top of each other or lay them on top of the background image, and that's going to give us the blur effect. And so I'm going to go ahead and demonstrate this. Now we have the blur filter right here and it's hooked up for us, but there are 2 other techniques that I wanted to go over that kind of deal with the extraction and then the layering process. So this first filter, what we're going to do is we're just going to isolate just the brightest elements in the scene, and this is called our bloom extraction technique. All right, so I'm going to go right ahead and look over to where we have our pixel shader. Now our bloom extract is actually pretty simple. And now we're going to be taking our color from the render target, and then we're going to be establishing some kind of threshold. And then we're going to subtract that threshold from the color. We're going to invert it, and then we're going to saturate it, meaning knock it somewhere between 0 and 1. And then what that will do is it will actually kind of like get rid of all of the stuff that isn't the brightest stuff, and depending on what our threshold is going to be. Or a different way that you do that is if you take the color intensity of the background. Now I have this commented out here, but I wanted to include that. All you'd have to do is take the color intensity and then you would multiply it or do a dot product against the grayscale intensity. If you remember, the grayscale product or the grayscale intensity is a vector that is kind of attuned to the human eye and it produces good grayscale value. We just take the dot product of that against our color value, and that's going to give us our intensity. And then if our intensity is greater than the threshold, then we're going to use that color. Otherwise we're going to return 0. So let's see what that all looks like. here is the slider that we have hooked up to our threshold. And if we start at 0, it's right there. But as we move the threshold up, you can see that only the brightest elements are being isolated, because everything else is going, pretty much drops to black. Then we take the result of that and then we put that into our blur filter. And now notice here I've got a separate blur filter that's just going to increase my blur strength. And so that's just going to create a certain amount of blur. Okay, then what we're going to do then is then layer that on top of the image, but we're going to adjust the bloom's intensity and its saturation. And then while we're at it, we're going to play around with the scene's intensity and the scene saturation. So let's take a look at that shader. So here's our composite shader. It's actually pretty simple. So what we're going to do is we're going to render our background texture, which will be our scene color, and then we have the result, our bloom color, which is going to come from our Gaussian blur. And then all we're going to do is just, we're going to, adjust saturation. Yeah, we're going to need to show you that. Okay, adjust saturation is we're going to convert the thing to the grayscale. So we're going to take the dot product of our RGB value and then do a dot product with the grayscale vector. And then we're going to do a simple lerp between our first color and then our second color. And then we're going to use whatever the, we're going to use the amount of saturation as a kind of variation between that. And so what that does is it basically adjusts the saturation of the scene. Because whether we're going to knock it down to a full value or we're going to keep it very, very simple. Okay, so we're going to adjust the saturation between our scene color and the scene saturation. And then we're going to do the same thing with our bloom color. And we're going to modify the saturation of our bloom color and the bloom saturation. And then our scene color is just going to be, we're just going to be doing a keying. Here it is, that A over B product, and this is it, gang. It's scene color times equal 1 minus saturate bloom color. Yeah, you've seen that formula before a bunch of times, and that's because it is the old A over B scene color. And so that's what we're going to do is we're just going to add our bloom color to our scene color, and it's going to be knocked into there, and so therefore our final value is going to be pushed right on top there. And like I said, we can control the bloom intensity. We can make the bloom really, really bright, or we can bring it on down, bring the intensity down. We can control its saturation. We can like bring it up to bring it down to gray, or adjust the saturation. And we, if we wanted to, we could do our background as well. We can make the background go a whole lot brighter, or bring it on down, and then all we can see is our bloom. Or we can play with the saturation of the scene, make it look gray, or make it full and vibrant. All right. So more or less, blooming is a way of kind of like making everything in the scene kind of look more fancy. It's a way of drawing attention, and it's something that the art directors really love to play with. And if you go ahead and implement bloom, it's not too hard of a shader, and you can implement this yourself in a couple of passes. If you implement that for your art director, they're going to appreciate it, and they're going to thank you for it. All right, well, that's all I wanted to discuss today. And let's see, we're going to continue our conversation for color filters next week, as we're going to go on 10/15, which is halfway through the month again, at 12:30. We're going to go talking about post-processing and otherwise just general function filters. And so I'm going to be going through, and I'm going to, instead of shader tool, I'm going to be going into UE5. Ooh. I'm going to go into UE5 and then show how to use the post-process or the customize filter in order to generate just kind of some random filters and function, and that's going to be a lot of fun. All right, folks, if you like what you saw today, go ahead and subscribe by hitting the little subscribe button down there. You know, check us out on YouTube or otherwise. My name is Chris Rhoda. You can check me out on Facebook and on LinkedIn. And if you're really feeling adventurous, go ahead and check us out on TechArt.edu. And you can see us on Facebook and on LinkedIn. Or if you're really, really adventurous and looking wild and say, hey, man, I'm not going to go to Halloween Horror Nights tonight. I'm going to go check our TechArt.edu Yeah, if you're that person, go ahead and check out the techartedu.com website. And there's a little opt-in button there. Go ahead and hit that opt-in button. Leave your name and your email address, and I'll make sure that you get updates whenever they happen. So thank you very much for joining me today. I look forward to joining you again next week for our last of our visual effects series inside creating post-process filters, and we're going to be doing that inside UE5. And until then, arrivederci.